Hello everyone, welcome to my talk. Thank you very much for coming. My name is Timur Doumler. I'm also known as Timur Audio on Twitter. I'm developer advocate for C++ tools at JetBrains. So if you want to talk about C-Line, the IDE, or ReSharp by C++, please come find me. This talk is called C++ Lambda Idioms. And there's kind of two different things I want to do in this talk. On the one hand, I want to kind of dig a little bit deeper into how Lambdas actually work under the hood, and some kind of traps you can fall into with them, and also how the way they work changed from C++ 11 to 14, 17, and so on. And the other thing I want to do in this talk is to talk about certain idioms or patterns that I've seen people use when they program with Lambdas that I found interesting or helpful. And I have one ambitious goal for this talk, is that every one of you, even if you're an expert, should hear at least one thing about Lambdas in this talk that it didn't know before. So let's see if you manage to do that. So Lambdas exist in C++ since the C++ 11 standard, so that's already actually 11 years ago. Here's an example. We have some kind of vector of people, and we call some kind of algorithm on it. In this case, we sort it, and many of those algorithms takes functions as parameters, so you can pass a predicate, like sort takes an optional comparison as a predicate. And in C++ 98, we had to pass in either a row function pointer or write a struct with a call operator, or if anybody remembers boost lambda and other kind of macro-based solutions. Since C++ 11, we have this lambda expression syntax with the square brackets, and I'm kind of going to assume that you know the basics, you know how this works. I'm not going to explain lambdas from scratch here. And so instead I'm going to dig a little bit deeper into what's actually going on here. And the C++ standard actually defines quite precisely what a lambda expression means and what it does. So if you read about that, it says that for each lambda expression that you write, it creates a closure type, which is a class type with certain properties. And that closure type has an inline function call operator. So if you write this lambda that we just saw, this lambda expression that we just saw in the previous slide, at the top is kind of the code that you wrote, and at the bottom is some approximation of the code that your compiler generates under the hood. And you're going to see here that it creates this closure type, which is a class. It has some kind of name which the compiler generates, which you cannot utter. That's why I put underscore underscore something something there. It's kind of internal, compiler internal name that you cannot use yourself, but the compiler knows about. And that closure type is going to have an inline call operator, and the body of that call operator is going to be the body of the lambda expression that you wrote. So the compiler is going to generate this closure type, and then it's going to create an unnamed temporary instance of that closure type. And then you can do with that whatever you want. A few things to note here. The call operator of the closure type by default is const. So this is one of the examples where C++ actually got the defaults right. It's const by default. If you want it to not be const, you have to actually explicitly write mutable there. Otherwise, it's going to be const. Another interesting thing is that the return type of this call operator is going to be deduced automatically for you by the compiler. However, you can also specify it explicitly with the trailing return syntax. It's not no except by default. You have to write no except if you want it to be no except, otherwise it's not going to be no except. Another kind of weird thing is that you can actually add an attribute to it as well, like no discard or deprecated or whatever, but for some weird reason, if you write no discard onto the lambda expression or some other attribute, that attribute is going to not be applied to the call operator, but it's going to be applied to the closure type. And actually, kind of the standard attributes that we have in the language right now, they're not really useful when you slap them onto a type. So none of this will actually work. It's not going to compile, and I really don't know why this has been done like this. Maybe somebody else knows. It's kind of unfortunate, so you can't really use attributes here, but it is what it is. So this is here the closure type, and we have kind of an unnamed instance of this type. And there is a little bit more going on, not just this call operator. So at least in C++ 11, the standard says that also that closure type has a deleted default constructor, so you cannot default construct a lambda. And it has a deleted assignment operator, so you cannot assign them either. And then if your lambda has no captures, so if this square bracket list is empty, it also is implicitly convertible to function pointer. Which means if you have some kind of legacy APIs, like a C library or something that accepts a raw function pointer, you can just pass in a lambda as long as it doesn't capture anything, like here, and it's just going to work. And that's, I think, pretty cool. And again, the standard says pretty precisely what actually happens under the hood there. What the compiler generates for you is a conversion function to pointer to function, which means this is, again, not the code you wrote, but the code that the compiler kind of generates under the hood or some approximation of that. It's going to create an inline conversion operator to function pointer, and the type of the function pointer is going to match the signature of the Lambda expression that you wrote. And the body of that function pointer conversion operator, what is going to happen there, it's going to return the address to a function, to a static function, which has the same body as the call operator. It has the same body as the Lambda that you wrote, basically. So that's what's actually going on under the hood there. And now that we know that, we can come to our first Lambda idiom, which is the unary plus trick. And I'm sure some of you have heard about it, but maybe some haven't. It's, I think, quite a curious thing. So we saw that lambdas, as long as they don't capture anything, implicitly convert to function pointers. But what happens if you want an explicit conversion to function pointer? And what that means is, let me actually switch. I have here C-line running, so I'm going to do some live coding. I've never done this before at a talk, so let's see what can possibly go wrong. Let's say we have a lambda here. I don't know. It's going to take an integer and then kind of return, I don't know, the square root of that integer, something like this, right? And we want this f, this variable here, we want that to be a function pointer. Okay, so we want to explicitly convert. So in other words, what you want is if you have a static assert of, is same type, is same v, decal type of that f, and then the function pointer type that you want, that should pass. Obviously, it doesn't pass. The error message says here, well, lambda something something internal type that you cannot name is not the same type as function pointer to a function that takes an int that returns an int. So what you could do is we could, explicitly cast it. We can write static cast, int blah 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 and so on, but that would be probably very long. You can write it much simpler by just adding a plus here. And that actually compiles and runs. Yes. Why does this work? It works, well, because unary plus operator is actually not defined for lambdas. It doesn't do anything for lambdas. It doesn't exist for lambdas, but it does exist for function pointers. So your lambda is going to be implicitly converted to a function pointer, and then the unary plus is going to be applied to that function pointer, and it does exactly nothing. A unary plus operator applied to a pointer doesn't change the value of the pointer. So what it is just a shorthand for an explicit conversion to function pointer, which I think is kind of cool. So that was our first little trick. Let's continue with the slides. Another thing that lambdas have are captures. And again, I'm not going to explain everything from scratch how captures work. I'm kind of assume that you already know that, so that's not a total beginner talk here. You can capture variables by value. You can also capture them by reference. You can also capture them with some kind of mixture of values and references, right? If we here capture two variables by value, the I and j, what is the code that the compiler is going to generate under the hood? And it's going to be something like this. It's going to create your closure type, and it's going to create, for each variable that you capture by value, it's going to create private members. I put the name __ I because it doesn't actually have the name I, the actual member, so you cannot name the member of the lambda directly. You cannot say my lambda dot I, that's not going to work. In fact, the standard says that those data members don't have names. And also it says that the declaration order of those members is not specified. So it's not necessarily the same order in which you have to find them in the outer code when they're captured. And if you capture by reference, it's kind of similar. You also get kind of reference members that your Lambda gets, that your closure type gets, that the compiler creates. Except here, the compiler has even more freedom. The standard says that it's actually unspecified whether additional unnamed non-static data members are declared if you capture reference. And that's kind of, you have even more freedom, and that's the case because it gives the compiler opportunity to optimize. For example, if you have two variables that you capture by reference, but you only ever use like the first one, and then the second one, you don't use them like at the same time, then the compiler can just create one pointer under the hood and kind of reuse that for both variables. So there's cases where you can do optimizations like that, and kind of this specification allows the compiler to do these kinds of optimizations. Again, remember the call operator of a Lambda is always const, so if you capture by reference, you can modify the value of those objects that it's referring to, but if you capture by value, then you cannot do that. You cannot modify the value because a const member function cannot modify the value of the members of the class, right? Another thing, you can capture this. For example, if you have a Lambda inside a member function of a class, you can capture this, and then what happens is that you're going to get a private non-static data member of this pointer, and then whenever you call a member variable of that class inside the Lambda, it's going to be transformed to a call through this pointer. Actually, the rules for this are kind of quite subtle. You know, you can also, there's also ways in which you can capture this by value, and what happens if you do this, what happens if you do that. It's kind of tricky capturing this properly and the different ways in which you can do it. And also the rules for that actually have changed throughout the different standards. So it's a bit of a rabbit hole. I'm not going to go into this here. If you're wondering about capturing this correctly, you can look this up. I'm going to talk about some other gotchas when it comes to Lambda capture, which I kind of discovered, which I found actually more interesting. So one really interesting property of capturing variables in a Lambda is only local variables get captured. If something isn't a local variable, it's not going to get captured. So if something is a static variable, even if it's only accessible locally, a static variable is not a local variable. Therefore, a static variable doesn't get captured in a Lambda. Therefore, if you have a static variable like here, you think you're capturing it by value, but you're actually not. If you increment the I inside the Lambda, you're going to find out that the value has changed outside. And that is because you're not actually capturing it, because it's not a local variable. You're just accessing it. So that means you can actually leave out the capture, and it's still going to work and still going to do the same thing, because you're not capturing it, right? You're just accessing it. Same thing with global variables, which I hope you don't have in your code, but it's actually exactly the same mechanism. You don't capture global variables. You can just directly access them from within a Lambda. It gets even more subtle than that. Not only do you only capture variables that are local, but also you only capture variables that are ODR used inside a Lambda. So if you have a variable which is local and it's used inside the Lambda, but it's not ODR used, it's not going to be captured. For example, if you have a constexpr variable. So it has a value that is known at compile time. And then you access that inside the Lambda. If you just access the value, that value is not on compile time, is known at compile time, sorry, and that is not an ODR use. Therefore, you don't have to capture it, and it will still work. Right? Yes, question? You have to say what ODR is. One definition rule. ODR stands for one definition rule. ODR use. So accessing the value of a constexpr variable is not an ODR use, so you don't have to capture it. However, if you take the address of that variable, that is an ODR use, so then it doesn't compile unless you capture it, and you have to capture it by reference in this case. It gets even more subtle than that. If you have a const variable which is of integer type, that is implicitly constexpr, right? So again, if you have a const int variable, that is implicitly a constant expression, and if you just use the value of that, which is known at compile time, that is not an ODR use, so you don't have to capture it. However, if it's a float, that rule doesn't apply. So if the float isn't constexpr, you do have to capture it, otherwise you get an error that it's not being captured. So there's quite a lot of kind of traps here. So we talked about capturing now. Let's talk about something else. Let's talk about the second idiom that I'm going to talk about today, immediately invoked function expressions. Some people also call them immediately invoked lambdas. And I think that is probably the most popular idiom when it comes to lambdas that I've kind of seen used by people recently or in the last few years. So I'm pretty sure some of you or a lot of you are very familiar with this. But let me just talk about this, because I think it's such an important idiom when it comes to programming with lambdas. So what is an immediately invoked lambda? Well, we now have seen, if you write a lambda expression, what the compiler does, right? It generates this closure type, and then it generates an instance of that. So if we have this lambda expression, so that's what the compiler is going to do. Turns out we don't actually have to assign this instance of the closure type to a named variable. We can do something else with it. For example, we can just call it, right? So we have this instance of the lambda, we can just immediately call it, and then it's going to be executed. And then, because it's a temporary object, we're not storing it in a named variable, it's just going to do pff, and just go out of scope, and that's it. So this program actually is just going to print hello world, and that's all it's going to do. It's probably not a straightforward way to write hello world, you might think, but actually this pattern of immediately invoking lambdas is super useful in quite a few cases. One of those cases is initializing a variable. So we have an object here, foo, and we want to initialize it. And it turns out that the initialization code for that object is quite complicated. It's not just a value. We have to write some code. There's some branches there. You have to check if you have a database. And if yes, we have to initialize it to something, otherwise something else, right? You have a little bit of code going on. So how do you do this? The way it's here on the slide, it's not actually that great, because we do this kind of two-step initialization, right? We first declare the variable without initializing it, and then we're initializing it later. In between, it has some kind of indeterminate state, potentially undefined behavior if you access it in between. Not a good idea. It kind of becomes more difficult to reason about it, and also kind of less safe. And also it doesn't work if foo doesn't have a default constructor, right? Then it's just not going to compile. And it's also not going to work if you want foo to be const, because you can't assign to a const object, right? Actually, this is different in Java. Java has a final keyword, which actually says you can assign to it exactly once, and that's going to do the thing that you want here, but we're not in Java, we're in C++. And in C++, if you have a const object, you have to initialize it where you declare it, right? So that's not going to work. So how can we fix this? Well, we could factor out, we could write it in a ternary expression. If you have something very simple, that might work, but that gets very ugly and complicated very, very quickly, so probably not a good idea. Another thing we could do is we could factor out the initialization code into another function, right? That's maybe sometimes good. Factoring things out into a named function, that's sometimes a good idea. But sometimes it's not, because your code is less local, right? You want the initialization to happen right there, but now you kind of removed it from the code where you're doing it. You have the logic scattered across different places in your code. And then also, if that initialization depends on some local variables inside main, you now have to pass these local variables as a parameter to the initialization function, so things get more complex. And it's just not a great solution. And it turns out, well, immediately invoke lambdas to the rescue. You can write it like this, right? You can put your initialization code in a lambda. You can, that lambda returns the value that you want to assign. You can immediately invoke that lambda, and then you can assign the return value to your const object, right? And that works, and I think that looks a lot better and pretty much solves all the problems. So that's the immediately invoked lambda pattern. It works not only for initializing objects, it also works very well for emplace back and make unique and make shared and all kinds of things like perfect forwarding. You can just stick a lambda in there, immediately invoke it, and yeah, it works really well. People say that one downside of this is that the fact that the lambda is called, like this paren at the end, is kind of a little bit invisible sometimes, or not invisible, but hard to see, right? Because there's so many places in the standard library and in other libraries where you pass in a lambda, you pass in a function. So it's a bit difficult to see that what's going on here is we are not passing a lambda. We have a lambda, we call it, and then we pass in the value that it returns. So it's a little bit difficult to see if you just have this paren at the very end. So one way we might fix this is we could instead write std_invoke. Std_invoke is a function in the standard library, which we have since C++ 17, which literally just takes the functions and calls it, right? That's pretty much all it does. But it's a little bit more visible, right? And so you can put it at the beginning, like it says std_invoke. So it makes it a little bit more obvious that what's going on here is that that lambda is being called. And that's, I guess, a matter of code style, which one of the two you prefer. And with these immediately-invoked lambdas, you can do more complicated stuff. And there's one idiom here which I saw in Daisy Holman's talk. Daisy, are you here? I don't think she's here in this room right now, but that's a CppCon talk she gave last year at CppCon. Here's a QR code with a link to that talk. I highly recommend you see that. And I think she has part 2 of that talk actually here this week. So I'm very much looking forward to that. So this is a trick from her talk at CppCon. And it's a very interesting use case for a immediately invoked Lambda. And what's going on here is that you want to have a piece of code that is called exactly once during the lifetime of your program. And I want to show this again in the IDE. So we don't need this stuff anymore. Let's say we have a class, right? And then that class has some kind of constructor. And then we have some snippet of code here which we want to be called only once, okay? And that's really useful. For example, I have a library where I have a type, and it does some stuff that depends on a particular CPU instruction being supported on the user's machine. So that's something that I need to check at runtime. But I only need to do this once during, like, whenever you first use one of those things, right? So this is a good use case for this. So it actually does come up in practice. And so how do we make this piece of code being called exactly once? Well, first of all, we can wrap it in a Lambda. And then one thing we could do is we could, so the Lambda has to return some kind of value, but it doesn't really matter what value that is. Oops. And then we're going to immediately invoke this Lambda. And then we're going to assign that to a static, local, well, not local, to a static object, right? And the name of that object doesn't really matter. And so now, we can create an x, we can actually create another x and even more x's. And if you then run this code, you see that that code is still being called only once, right? Yes?
This is also thread safe.
Yes, I'm coming to that. So what's going on here? I mean, people who have read Scott Meyer's books and are familiar with the Scott Meyer's singleton, they know already what's going on here. So a static object is guaranteed to be initialized only once, even if it appears in a function that's being called multiple times, like this constructor here. So no matter how many x's we generate, this is the static object is only going to be initialized once. And actually it has another interesting property. It's guaranteed to be thread safe, right? So we can even create those objects of type X from multiple threads simultaneously, and it doesn't matter. Like, the compiler will make sure it's thread safe. It's going to insert locks as appropriately. So you're guaranteed to have this code executed only once and thread safe way. So I think that's really, really cool. This is something that Daisy showed in her talk, and I thought that was really interesting, very interesting technique. So actually, the standard library does have a function called std_call_once, which is doing exactly this. But Daisy found that if you do it manually like this with Lambdas, for some reason it's a lot more performant. And yeah, I think that's interesting. And I also think it's interesting that it's just an interesting way to use Lambdas, right? It's an immediately-invoked Lambdas. So I think even if you might find that you can just use std_call_once, I still think it's interesting to know that you can do this kind of stuff. So I think that's a really cool trick. Let me go back to my slides here. So we talked about the call once Lambda, and now we're pretty much done with C++11, and we move on to C++14. And in C++14, we got another really big feature, which is generic lambdas. So we got generic lambdas in C++14. What are generic lambdas? Well, in C++11, you had to spell out the type of your parameter in the lambda. In C++14, you can just write auto, and the type of the parameter is going to be automatically deduced for you using the usual rules of template argument deduction in C++. And that's really useful. For example, here, we have a predicate on a std map, and we probably not everybody can spell out the correct element type of a std map on the first try, but we don't have to because you can just write auto and the compiler is going to deduce that for us. So that's really cool. What's going on actually here under the hood? If we have a generic lambda that takes an auto parameter, the compiler is going to generate something approximately like this, where now the call operator of that lambda is a template. And that's really important. When I was learning C++14 and I learned about generic lambdas, for a while I thought that the lambda itself would be a template under the hood, and that's actually not what's going on. The lambda is not a template. The closure type is not a template. The call operator is it's a function template. That's what's happening there. That's really important. So if you understand that, you understand pretty much how generic lambdas work, and we're going to see this later as well. And if your generic lambda is not capturing anything, you still also get the implicit conversion to function pointers. So your compiler will still also generate this conversion operator to pointer of function, but that operator is now also going to be a template. And that's also really cool, because if you have your legacy C API and you can pass in a generic lambda, and that works, and the compiler knows what type you want there, and it's going to correctly call the right conversion to function pointer for you. So the implicit conversion will work. However, the explicit conversion with the plus, that trick doesn't work anymore with the generic lambda because the compiler doesn't know what type it should convert to, right? So that is not going to work anymore. Generic lambdas are great. If you write autoref, you get forwarding references, right? So the compiler generates this code where you have template type name t and then tref. That's a forwarding reference, so that's going to work with all kinds of perfect forwarding stuff. It also works with parameter packs. That's really great, which means you can write variadic lambdas. That's really, really cool. What else? Oh, yeah, it makes it really easy to pass lambdas into other lambdas and do kind of higher level functional programming with lambdas. So you can do really fun stuff. You can have a lambda that takes a lambda as a parameter and then returns another lambda that calls the first lambda twice, and things like that. So if you're into functional programming, you're probably going to see how you can have a lot of fun with this, and kind of auto parameter just makes this stuff really, really easy to write. And we're gonna see some of this later too as well. Another feature that we got in C++14 is init capture. And init capture is also really cool. So in C++11, you couldn't capture a move-only type like std unique pointer, for example, by value, right? Because capturing by value means you're copying the value into this private non-static data member that the compiler generates for you. But you can't copy a unique pointer, so it's not going to work. Well, in C++14, you can just do this. You can basically create a new variable in the capture, and you can just move the unique pointer into it there. And it can have the same name as the variable that you're moving into, but it can also have a different name. It doesn't really matter. And what happens under the hood is that if you have an init capture, you're initializing a variable, the compiler is going to deduce the right type for you based on the initializer. It's going to create a private member, and it's going to initialize that when you create the lambda. When you write the lambda expression, it's going to initialize that member accordingly with whatever is on the right-hand side of the assignment. And that is really cool. There is actually another idiom here, which you can use this for. You can use init capture to optimize things. Now this is, and again, every time I have a QR code, this is like a link, so you can check this out. This is from a book by Bartłomiej Filipek, C++ Lambda Story. It's a really, really cool book. I can definitely recommend that. If you want to dig deeper and like read a little bit more about the details of how it all works, like it's a really good resource. This is kind of a technique from that book. It doesn't really matter too much what exactly is going on here. We have some kind of vector of strings, and then we have a const string variable here, and we are running std_findIf on that vector, and then we are passing a lambda in it, and that's going to be the thing that it's going to be looking for, right? It's going to be the predicate. And in that lambda, we're capturing this string prefix, and then we are doing something with it. And specifically, we're appending another string to it, which actually is going to create a new string object that's overhead, right? It could be another allocation and stuff like this. And because that lambda is being passed into a find if, that's going to be called every time around in the loop, right? So, but that's kind of the result of that computation is going to be the same every time around, but we're going to call it multiple times. And that's not really efficient. In C++14, we can instead just do that computation once, store it in a init capture, and then just access that inside the lambda. And then we're going to save precious CPU cycles. So I think that's a really cool kind of technique that you can use init captures for. All right. We're done with C++14. We come to C++17. C++17 brought us even more things we can do with lambdas. It's really, really cool. So lambdas can now be constexpr in C++17, so you can use them. For example, you can use the result of a lambda as a non-type template parameter. You can use them for all kinds of other compile time metaprogramming as well. That's really cool and powerful. And we have another feature in C++17 which is called class template argument deduction, or CTAD. What CTAD is basically you don't have to, if you have a class template like vector, you don't have to write the template arguments anymore. You can just write std vector, and then it's going to deduce std vector int, the template arguments from the initializer. You might think, well, what does that have to do with lambdas? But actually, it has a lot to do with lambdas, because this brings us to our next idiom, which is the lambda overload set. And that's, I think, my favorite lambda idiom from all the ones that I'm going to be talking about today. I think it's just really, really cool. It kind of brings together various techniques in modern C++ in a really interesting way. So I'm going to show the lambda overload set again in a live coding session. Let's see how that goes. So what we're going to do here is, what you want to do, let's remove this, we don't need this anymore. So we want a lambda overload set. So we want to have an object which holds an overload set of a bunch of functions. And then, you know, if you call it, and that object itself should be callable as well, like a lambda, it should have a call operator. And if you call that object, it's going to select the right overload for us, depending on what we have passed in. So, and we can do this with lambdas in a really cool way. So the first observation is that we can take a bunch of lambdas together and we can inherit from them. Because, yes, because a lambda has this closure type, and we saw what the compiler generates, right? It's this like unnamed closure type, but it's a type, it's a class type. If it's a class type, you can inherit from it, and then you can say, using operator paren in order to use its call operator, right? You can do that. And because lambdas are classes, it works with lambdas too. Of course, you can't name the type of the lambda, so you can't just say, I'm going to inherit from this lambda. That's not going to work because you can't name the type. But what you can do is you can write a variadic template. Let's call this overload. And then we can inherit from all those types, right? And then we can say, using operator, call operator. So now we have inherited from a bunch of classes, and we're going to inherit the call operator of those classes as well. And please observe that this is an aggregate. And the elements of that aggregate are its base classes. And if it's an aggregate, we can initialize it with aggregate initialization and list what base classes you want to have. So we can say autof equals overload, and then give it a bunch of lambdas. And so we can give it a lambda for I, and it's going to do, I don't know, some stuff with integers. We can give it another lambda, which takes a float. It's going to do some float stuff. And if you now call that with an int, it's going to do the int thing. And if you call that with a float, it's going to do the float thing. Okay? And cline is giving me a squiggle here because in C++ 17, we didn't have ctat for aggregates yet, so we would have to write an explicit deduction guide, which is another 2 lines of code. But since C++ 20, we have ctat for aggregates, so we don't have to write the deduction guide anymore. And actually, here I can show you I'm using the latest Microsoft compiler here as my toolchain, and that is the one compiler I found that supports all the features that I'm going to talk about in this talk. The other, like Clang and GCC, they don't, so that's why I'm running this here in this weird setup where I have a Mac and then I have a virtual machine, and this is like Windows and cline running on Windows, running the Microsoft compiler because the Microsoft compiler can actually handle all the code that I'm throwing at it. So please ignore this red squiggle. This is correct. So we have this overload set here, and I think this is really cool. We can do even more cool stuff with it. So it works really, really well with variant. So if we have a variant of int and float, and let's just initialize that. Oops. Right, so I need to include the header here. And then I can write std_visit f2, and if the variant, oops, what's going on here? Oh, sorry, fv, right? So if the variant is currently holding an integer, it's going to do the int thing, and if it's currently holding a float, it's going to do the float thing, okay? So I think that's really, really cool. And it's all made possible by this little trick up here. And yeah, if you do want to know what the deduction guide looks like, if you do have a C++ 17 compiler and no C++ 20 compiler, you kind of have to write this 2 lines of code here. And now you see that the red squiggle here went away. So Clang now also understands, because Clang is the thing that's used here to produce the red squiggles, and Clang now also understands that this is actually valid code. But in C++ 20, we don't need this anymore. Right? All right, so I think that's a really cool trick. Let's go back to our slides. And let's talk about C++ 20, which is the current standard. Right. So in C++ 20, we have a bunch of new stuff. Lambdas can now capture structured bindings. Lambdas can now capture parameter packs. You can now define a lambda as const_eval, which means, you know, if we mark it as constexpr, we can use it during constant evaluation at compile time. If we mark it as const_eval, we can only use it at compile time during constant evaluation and not at runtime. So if you mark a lambda as const_eval, you can still use it, for example, during like meta programming for a non-type template parameter, or you can call it with a constant expression like 5. But if you call it with something that's not a constant expression, but like a runtime thing, like a variable x, that's actually going to error out. It says like, I can't evaluate that at compile time. And then there's 2 other cool things, actually 3. Lambdas in C++ 20 are allowed in unevaluated contexts, such as, for example, decal type. And if lambdas have no captures, if they're stateless, we can now default construct them and assign them. And that is really, really, really cool, especially the combination of those things. So there's quite a lot of things that we just couldn't do previously. So for example, previously we couldn't have a data member that is a lambda, unless you had template on it, and it could be anything. But like, you can't write out a data member that is a lambda, because you would have to write auto because you can't spell the type. But you can't have a data member that's auto because you need to specify what them, like if you declare a data member, you need to spell out the type, right? Because the compiler needs to know what the layout of that class is at compile time. So you can't do that. But in C++ 20, you can instead do this. You can spell the type by just saying decal type that lambda, and then you can just create an instance of that. And that's going to be default constructed. And you might think this is probably not very useful, but it's actually super useful. It comes up all the time because one of the things where it comes up is every time you have a template parameter that takes a function. And that comes up a lot in a standard library. For example, std_unique pointer has a second template parameter, which is a function, which is the deleter. You can specify custom deleter. So you can pass the deleter kind of as a constructor argument, kind of, yeah, but kind of at runtime. But we can, in C++20, what you can also do is you can just specify it in the type, right? You can have a type def and say, the deleter is just decal type of that lambda, and that's just the type of that deleter. And then every time, you can just create those unique pointers, and they're just going to be default constructed because it already knows, yeah, this is the kind of deleter you want. You gave it the type of the lambda, and it's kind of just default constructs those lambdas from that type. Set is another example where the second template parameter is a comparator, and again, you can write out your comparison in a lambda and wrap it in decal type and just put it in the type def, and that's it. Another thing we have in C++20 now is templated lambdas, and that's generic lambdas, like here, but instead of writing auto, you can now explicitly specify the template parameter. Right? You can spell out the parameter, the template parameter list, and it lets you name the template parameter. So you have access to this like type T now, and that's really useful. So for example, here we have a vector of integers, and we want to remove all the even numbers, right? And so kind of that works, but what if it's a vector of float? And now you get this error message, yeah, invalid operands for binary expression. So it kind of errors out somewhere in the body of that lambda. But if you have access to the parameter of that lambda, the template parameter, you can use all the things you can use template parameters with. For example, you can write a constraint and use concepts. And you can say, well, this lambda requires that the type is an integral type, right? And then you get a much, much better error message. So it allows you to program with basically the types, the parameter types of the generic lambda. I think that's really, really cool. And that's what C++20 gives us. And now we're pretty much done with the C++ that we have today. But of course, we have an upcoming standard, C++23. It's not out yet. We're still working on it. We still have a couple of meetings to go, but it's looking good, and it's going to be ready next year. But we already know that it's going to have a really cool language feature in it, which is called deducing this. Who has already heard about deducing this? Okay, quite a few people. I'm going to very quickly describe what that feature does. I think it's the most exciting core language feature in C++23. It's really, really cool. It comes up in various ways. One of the problems in C++20 and before is that there are these situations where you have to overload on whether the object itself is an R value reference or an L value reference, or it's const or it's not const. And especially if you write generic code, for example, here, if you're implementing std optional value, you basically have to write out all 4 overloads because they kind of return slightly different values, but it's all the same code. It's doing exactly the same thing, but you have to like spell it out 4 times because you need to define those 4 overloads. So you end up either quadruplicating the same code, or, I mean, there's not really a good fix for this in C++20 and before. The other thing you could do is you could have like 1 of the 4 having the actual code, and then the other 3 overloads kind of refer to it, but then you have to write all these ugly casts to like make sure that the kind of value category and like constness is correct for each one of them. Or you can delegate it to a private kind of impl member, and then all 4 overloads have to call that thing, which again is kind of ugly. So there isn't really a good solution for this, but in C++23, we never have to do this again. We can just write one function. What deducing this gives you is you can say that you can basically write this, the keyword. This syntax kind of looks a little bit weird. You can write this keyword in front of a parameter declaration, and that means that this parameter is going to be this object itself. So it's going to be a bit like in Python, where you kind of can pass self as the first parameter explicitly. And that's exactly what we can do in C++ here now as well. And that gives us the power of template argument deduction, right? So now we can deduce whether or not it's const or not const, or what kind of reference it is, or whatever, and it makes it a lot easier to program with this. So we only now need to write one function instead of 4. And actually, this is the long syntax. There's also a short syntax. You can just write this auto. This comes up, this is very, very, very helpful for not just this, but there's quite a few other use cases where this is great. For example, it makes CRTP a lot easier, and I encourage you to check out the actual paper, the proposal. Again, link is here in the QR code. But we're talking about lambdas. So what does this have to do with lambdas? And it turns out, one of the side effects of this feature is that it makes it really, really easy to write recursive lambdas. And that's what we're going to do now. Okay, so let's think about how would we write a recursive lambda. And we're going to use factorial. This is like the canonical example of writing a recursive function, right? You should not actually implement factorial like this, but let's just use it for purposes of our little presentation here. So how would we implement a recursive factorial with lambdas? Well, the naive approach, right? So you write a lambda, it's taking an integer, and then, if that integer is 0, you return 1. Otherwise, you return that integer times recursive I minus 1, right? So this hopefully is not surprising to anybody. And then we want to print the value for 5, for example. But it doesn't work, right? Let me actually move this up here. It doesn't work, right? Because you get this nice error message here. You cannot refer to a variable before it's been declared, right? That's just not going to work. So we can't do this. What can we do instead? Well, we can cheat, right? We can say it's just a function. And then we have to include the header again. Oops. And then we have to capture that f by reference. And now it works. Right? This is like C++ before 23, right? You can write this today. But it's not great, right? So the function has quite a lot of overhead. It has type erasure inside, which is indirection virtual functions. It probably might even allocate memory. We don't want that. What can we do instead? Well, okay. So we can't refer to f from within f. But maybe we can template on the thing that we want to refer to, right? So we have generic lambdas in C++ 14. So we can say, okay, let's pass in self, and then let's call self on itself. And that doesn't quite work. We need, annoyingly, a helper function now, so that we can actually tell the function that it should call itself with itself, right? So we need to write this thing recursive, and it's another lambda, and it's now a higher level lambda. It's going to take a lambda and a number, and it's going to call that lambda kind of on itself. Okay. And now we have to also call this helper, right? And that don't work, okay? It gives us 120, so that's good. But nobody's going to write it like this, right? This is kind of an advanced technique from functional programming. It's called a Y combinator. It's kind of really cool, but it's way too complicated. It's not a practical solution to the problem. Turns out, in C++ 23, with deducing this, it's a lot easier. You don't need this thing. You can just write this here and call it normally as we did before, and now it's going to work. Oh, and I don't need this anymore here either, because that's just implicit, like this, the implicit first parameter. We don't need to explicitly pass it. And that's going to compile and run and gives us the correct result. I still get these red squiggles here because C-line doesn't actually know about the syntax yet. We're hopefully going to fix this very soon. But the Microsoft compiler that I'm calling here does know about this feature. So that looks a lot better, right? We are just calling it recursively. And you might think, okay, this is cool, but it's just like a toy thingy, right? Like, why would you actually call recursive lambdas, like in practice? Like, what practical engineering problem does it solve? Well, it turns out, actually, this is super useful. And this is something I learned from Ben Dean, who gave another excellent talk at last year's CppCon called Deducing This Patterns, where he just presented all the different ways in which deducing this is going to make our lives a lot better and easier. And I recommend you check out this talk. And one of the things he showed there is this technique where you actually combine two idioms here. I think that's also really cool. You can combine them, right? So we're now combining the lambda overload set that we saw previously and the recursive lambda technique that we just saw. And this is the example from Ben Dean's talk. We now have here a tree, and we implement this as a subvariant. And what we want to do is we want to traverse the tree and count the leaves, right? Of tree traversal, right? Classical kind of engineering problem. And we can now implement it with the techniques that we just saw, right? So because it's a variant, it's kind of invites us to do the lambda overload set Deducing technique that we saw before. So we now have the already familiar overload thingy here. And with that, we can call setVisit and give it an overload set and say, well, okay, for leaves, just return 1 because a leaf has 1 leaf. And if you have a node, well, then we just do the usual thing of recursing into the node, and it's the number of leaves from the first subnode and the number of leaves of the other subnode, right? It's a binary tree, I should say. This is a binary tree. So it's a binary tree traversal. And the trick here is that we're actually calling the lambda recursively on itself when we do the node tree traversal, right? So I think this is really cool. This is, I think, a classic C++ job interview question, implement recursive tree traversal. So if you are preparing for a C++ job interview and somebody wants you to do this, you can really impress them by doing this. Although I would strongly recommend that you have a cutting-edge compiler, otherwise it's not going to compile. Right. So this is what we're going to be able to do with lambdas in C++23. This concludes the main material that I had, but however, we do still have 7 minutes left. So I think I can squeeze in some bonus material, and this is something that is from literally just last week. This is something really cool. It's an idiom that I learned from Björn Faller, whom I'm going to credit as the inventor of this. And I call it the variable template lambda. And I think this is really cool. So thanks, Björn, for introducing me to this technique. I think Björn was actually supposed to be here at the conference, and then he couldn't make the flight or something, so that's very, very sad. I was really looking forward to talk more to him about this here at the conference. But maybe in this way he can be here just in a little bit, because he came up with this. So remember how we said that if you have a generic lambda, which takes an auto parameter, under the hood what happens is that the compiler is going to generate a closure type, and then the call operator of that closure type is going to be a template, a function template, right? And it's really kind of important that in this case, the lambda itself isn't the template. Just the call operator is the function template. But what if there was a way to make the actual lambda a template? So this came up on Twitter a few weeks ago, where I was actually preparing this talk, and I posted a few things about the weird things that I found out about lambdas, and I was like, hey, this is some crazy stuff I learned about lambdas in C++. Post your favorite weird thing. And Björn replied and wrote this, and I'm just going to leave this here for a bit. He says, well, you can make a lambda a variable template and access the template parameter in it. And then he posted that little snippet of code. And again, the QR code is the link to the actual tweet. And I was looking at this and I was like, whoa, what's going on here? This is interesting. So what's happening here? So we have a generic lambda, right? And then we assign that lambda to a variable, and that variable is a variable template, right? Variable templates, it's a feature that we had since C++14, I think. I've only ever seen it before with things like template type name t, pi, and then it could be float pi or double pi or something. But yeah, we actually assign now a lambda to it, and a generic lambda as well. And then we can call it and specify the template parameter of that variable, right? I think that's really interesting. And then I wrote Björn an email and I said, hey, Björn, this is really cool, but like, can we actually use this for something? Like, is this useful? And then he wrote back to me and said, yeah, actually, I have a use case for this. And I was like, very interested in this. So before we get to that, actually, here's what I think more or less is what the compiler does with it. So there's like two different types of template parameters going on here, right? So we have the template parameter of the variable template. That's a template type name t. And that's going to effectively be a template parameter of the lambda, right? Because the lambda itself is now a variable template. So we have that. And then we have another template parameter, which is a template parameter of the generic lambda. And that's a different template parameter, right? So we now have a kind of templated closure type, and then that has a templated call operator, but it's a different template parameter. And here's an example that Björn emailed me, and that's, I think, is really interesting. So basically what you can do is you can kind of separate template parameters in like a very interesting way. So here we have struct time. Doesn't really, again, matter very much exactly what it does, but it has a variant inside. And then it has some kind of convert function where you can give it a convert function and it's going to convert the time to something else. And the important bit here is that this is a higher order function. So it's, again, a function that takes a function and then calls that function inside, right? And what if we now want to pass std chrono duration cast to this function as the thing that it should be using as the converter, right? So it can hold the time as milliseconds and nanoseconds, and then for some reason you want to cast it to microseconds. Turns out this doesn't compile, right? So we get an error, and the reason for that is that duration cast actually doesn't have only one template parameter, which is the one that you see here, but it actually has three template parameters, right? It has one template parameter, which is the duration you want to cast to. That's the template parameter you write. And then it has two other template parameters, which are being deduced from the argument that you give it, right? And the problem with function templates is that if you pass them as function pointers, you can only do that if you fully specify all template arguments, right? So that you make it into an actual function and not just a function template. So then you can take its address and pass it as a pointer, which is kind of what's happening here. But you have only written one template parameter, not three, right? So you've only specified one of them. So you can't get a pointer to that, right? It's not a fully specified function. So that's not going to work. And then here, Björn's variable template pattern comes to the rescue. And you can write this little wrapper around the chrono duration cast, where basically you say, okay, the first template parameter, the one that we want to specify explicitly when we define when you write the call, that's going to be our template parameter for the variable template. And then basically that is the first template parameter of duration cast, and that's the one you want to specify, so we make it a template parameter of the variable template. And then the other two template parameters of chrono duration cast, well, we can just deduce them from the thing we pass in, and we're going to use a generic lambda to just pass that through, right? So that's going to be a template under the hood, and the other two templates, that template parameter is going to be passed through to duration cast. And it's going to deduce the right template parameters when the visit calls it somewhere inside, right? And so you can basically separate out the template parameters that you want to specify yourself when you write duration cast microseconds on the one hand and make them a template parameter of the variable, and the template parameters that you want to be deduced automatically through function template argument deduction on the other hand, and make those the template parameters of the generic lambda. And you don't have to worry about those. So you can kind of separate that into two sets of template parameters. And that is really, really cool whenever you have a situation where you have a function taking a function, like a higher order function, and you want to pass a function template to it, and you want to use that function template with different template parameters inside the same higher level function. And that's when this pattern basically allows you to do that in this really kind of cool way by just writing a wrapper. So yeah, this is the last technique I have for today. That's all I have. Thank you very much for your time. And I'm not sure if you have time for questions.
So tricks can be tricky, right? So in the real life, like how do you weigh the advantage of using a useful new trick or new idiom against the possibility of misuse later on, or somebody doesn't understand what's going on in the code?
That's an excellent question. I think this talk is more about what you can do and how it actually works. It's not so much about what you should be doing. Because some of those, I mean, how do I put this? Like, I think it's really, really cool to like know about the mechanisms and know why these idioms do what they do. And some of them, like the immediately invoked lambda, for example. This is something that is already so ubiquitous that I think this one is definitely fine to use even if you have people who are not familiar with it, because I think it's becoming an idiom that you just kind of need to know if you're a C++ developer, right? Some of the others are maybe a little bit more tricky. I think the overload one is also, I think, I've seen it in code, the overload set one. This last one, it's more of a gimmick, so I think if you want to use it, you have these situations where it might save you, but like you probably need some kind of big comment there. This is what's happening, or I don't know. Like it's a tricky question, right? Because sometimes you shouldn't be using idioms just for the sake of using something cool so you look smart in front of your colleagues, right? So I think it's kind of I think time will tell like which of these idioms are going to become so popular that people are just gonna know them. I think some of them already are, others are probably not. So let's just wait and see. Some of the stuff like deducing this is such a new feature. Only one of the major compilers even supports it, and only in the newest version. I think not enough time has passed for us to be able to say, this is an idiom you should all be using, and this is kind of a nice trick, but like maybe too weird, and like you're going to like alienate your colleagues if you do that. So I don't have a good answer. I'm sorry.
Like seeing it then, as you say, of like maybe thinking of it as the evolution of a language, just like the evolution of English or any other language.
I think two aspects, like the evolution of a language and how it actually works under the hood, which makes you understand other things you might see elsewhere. Because if you know the underlying mechanism of lambdas or any other feature, it makes it easier for you to understand other idioms that you maybe haven't seen yet, because you just will know what's going on. You will be able to figure out what's going on more easily.